We're going to talk about the divergence of the curl of a vector field and also the curl of the gradient of a scalar field. So let's start with the divergence of the curl using subscript summation notation. Divergence of curl of A using subscript summation notation. This is the del operator, del xi ei hat dot product with the curl. So it's epsilon jkl, Levi-Civita symbol, del xk applied to L component of the A vector field in ej hat direction. So this is equal to del xi. Now we have two vectors, ei hat and ej hat. So we're going to take their dot product, ei hat dot ej hat, epsilon jkl del al del xk. Now we know that ei hat dot ej hat is Kronecker delta. So this is epsilon jkl Kronecker delta ij del xi del al del xk. Now we're going to set I is equal to j, so epsilon jkl will become epsilon ikl, and we have del xi del al del xk, and if we go in this order, epsilon ikl is epsilon kli. So we can notice that if I switch k and I, what will happen? This will be epsilon kil and del xk, because I have switched k and I, del al del xi. But now I notice that in doing so, switching k and I here, I have epsilon kil becoming epsilon ikl, or epsilon ikl becoming epsilon kil. But a switch of these positions, on the other hand, instead of changing the names of these indices, would imply that I have minus epsilon ikl, because I have an odd number of changes in the position, kil, ikl. So going from kil, I should do ilk and lki in the positive direction. So IKL is in the negative direction. So this is basically implying that what I have on the right hand side, epsilon KIL, is actually minus epsilon IKL del xi del AL del xk. So what I have done here is I have substituted for epsilon KIL minus epsilon IKL, and then I have changed the order of the derivatives because the order of the derivatives does not matter. So I can note here order of derivatives does not matter. Now I see that this value, epsilon IKL, partial derivative with respect to xi, partial derivative with respect to xk of AL, is equal to minus of itself. Epsilon IKL, partial derivative with respect to xi, partial derivative with respect to xk AL. So what does that imply? This implies the following. Divergence of the curl, divergence of curl of A must be equal to 0. Okay. Now let's work on a similar problem. This time curl of the gradient of a scalar field, curl of gradient of phi. So let's write down curl of the gradient using the subscript summation notation. This is now epsilon ijk, Levi-Civita symbol, jth component of the del operator, del xj, and then k component of the gradient of phi, and this is going to be in ei hat direction. So now I'm going to write epsilon ijk ei hat, and now partial derivative with respect to xj of the kth component of the gradient of phi, which is del phi del xk. And at this moment, I'm going to switch the positions of j and k. This is, or actually rename j as k and k as j. So ikj ei hat. This is going to become del xk del phi del xj. So what I have done is rename j as k and k as j. And now I notice that epsilon ijk is equal to minus epsilon ikj, because I have an odd number of switchings in the positions, and also the order of derivative doesn't matter. Is not important. So this means for epsilon ikj, I can write minus epsilon ijk ei hat, and this is del xj del phi del xk. Now comparing these two terms here, epsilon ijk minus epsilon ijk ei hat del xj del phi del xk, I have again the same thing equal to minus of itself. So this result implies curl of the gradient of a scalar field must be equal to 0. Now, for a vector field V, we can write a vector field V as V is equal to curl of a vector field A and minus the gradient of a scalar field phi. So here A is a vector potential and phi is a scalar potential. So we can decompose this vector field into two components, one containing the curl of a vector potential and the other one containing minus the gradient of a scalar potential. Now if you take this vector field and consider its divergence, because divergence of the curl is 0, we will get minus divergence of the gradient of phi. So that means divergence of V is equal to minus del square phi. All right, so this is true because we have divergence of the curl of A is equal to 0. On the other hand, if I consider the curl of V, since the curl of the gradient is 0, I will get curl of A. So curl of V is curl of A, because we have curl of a gradient of a scalar function phi equal to 0. We have just shown that. On the other hand, if I take the normal component of this vector, it will be n hat dot product with curl of a vector potential minus the gradient of a scalar potential, gradient phi. So what does this imply? If you have a vector potential A, scalar potential phi specified, then because n hat dot v is also written this way, the vector field V is uniquely specified by Helmholtz theorem. Helmholtz theorem tells me that if you know the divergence and the curl of a vector field within a certain region and its components along the normal to the surface that's at the boundary of this region, that vector is uniquely determined, and that's as a consequence of that, I can see that a vector can be decomposed into its vector potential and scalar potential parts such that A and phi will tell me uniquely what that vector is. The curl of A is called the rotational or solenoidal part, and gradient of phi is called the irrotational part of this vector field V. All right, so we talked about divergence of the curl. In divergence of the curl, first I have written the divergence as del del xi. I had dot product with the j component of the curl A, and then j becomes I because this is a dot product, Kronecker delta ij. So for the curl, we have epsilon jkl ej hat del del xkal, and first I have rewritten I is equal to j, so j has been replaced by I, so this is epsilon ikl del del xi del al del xk. Then I have renamed k and k as I and I as k. So this is basically what I mean by switch I and k, not switch their positions. So this becomes epsilon kil del del xk, because I has been renamed as k and k has been renamed as I. And because epsilon kil is equal to minus epsilon ikl, an odd number of switching in the positions, we find that these two things are the same, considering that the order of derivatives doesn't matter because I could do del del xi first and then del del xk. So I found that divergence of the curl is 0, and similarly I have found that curl of a gradient is 0 by doing the same trick, basically renaming j as k and k as j here, and then finding that epsilon ijk is minus epsilon ikj, because an odd number of switching in the positions of j and k. And then I have the order of derivative doesn't matter. Therefore, I find that these two things are the same with so x is equal to minus x implies x must be 0. So curl of the gradient of phi is 0. So that means I can write a vector field V as curl of a vector potential minus the gradient of a scalar potential, if I can find out what these potentials are, then this vector field is uniquely specified by Helmholtz's theorem. The curl A part is called the rotational or solenoidal part, and gradient phi part is called the irrotational part.